plus, right? So here we are, chromium 2 plus, right? Let's do it. Really good. Okay, so chromium is what kind of electron configuration for chromium? Let's see. Where's chromium? Over here. There. Right? So it's argon, and then what do we have? Argon means all the electrons are paired. Yes? Okay, so then from argon we'll go to what? 4s2 and 3d4. Okay. So it's what? Say it again without so I can hear it. 4 what? 4s2 and then 3d4. And that's argon, right? Like this. Okay, so chromium 2 plus, argon. Then I take it increasing first quantum number, so it's going to be 3d4, 4s2, and then we create the ion, correct? So now, this is going to be the atom, right? Then we create the ion, correct? So now we have chromium 2 plus, it's going to be the argon. This goes away, right? 1 minute. And it's going to be 3d4. 3d4. Who has a question? You? I thought Cherie, you had a question. Huh? 4s what? What's the charge of chromium? 2 plus, yes? The chromium is 2 plus. The E, the ligand is 0, correct? Yes? So chromium is 2 plus. So 2 electrons are gone, and the electron configuration was solved. Chromium 2 plus is what? A D4 system. Yes? A D4 system. Okay, now, that chromium 2 plus is not naked. It means it has a chemical environment. There's bonds to it. Right? With what? Ligands. 3 ligands. It's an octahedral arrangement, isn't it? We have a bidentate ligand 3 times. So you have 1, 2, 3. You remember that? 1, 2, 3. So you have coordination number of 6. Yes? Like this, look. Here is chromium. Right? Here is octahedral. So you have one like this. You have one like that. And you have one like that. Yes? Here is nitrogen, nitrogen. Here is one ligand. Here is nitrogen. Here is nitrogen, nitrogen, nitrogen. Here is one ligand. Here is another ligand. Bidentate, look. 2 teeth. Each one 2 teeth. You see that? 1, 2, 3. Coordination number 6. 2 plus. When you have this environment, all these 4 electrons, they are not the same energy. When it's free, like this, you have 1, 2, 3, 4, 5. Hund's rule. Hund's rule. 1, 2, 3, 4. You have 4 ampere electrons. When it's free, no chemical environment. When chemical environment comes in, octahedral chemical environment, then what happens? This become 1, 2, 1, 2, 3. Here is energy. Yes? 3 lower energy, 2 higher energy. Yes? And this is Ag. And this is G2G. And now I'm going to start putting them. How many there are? 4. 1, 2, 3. Oops. Now what I'm going to do with the 4th one? Will I put it here? Or I will put it there? Where I'm going to put it? Who is going to answer that to me? The ligand. The ligand is weak field or strong field? Strong field, that means it creates a big gap. Yes? So if this is huge gap here, look, this is large. Delta is equal to large. That means the electron does not like to go upstairs to the 20th floor. It takes a lot of energy. It does not like to go upstairs. It's going to pair. And then how many electrons are we going to have? Huh? How many ampere electrons? Everybody got it? Yes? Huh? No? Why you didn't understand? Let's talk about it later. Okay? Let's have some music.
Oh, no, I'm right. Hello. Yeah. My name's Fadi. I usually perform with my guitarist, Alan, but he couldn't make it tonight, so I'll be singing a cappella. I'm not all that great, so I'll try my best. Thanks. The song I'll be performing is Waving Flag by Qian. So here it goes. When I get older, I will be stronger. They'll call me freedom, just like a waving flag. So wave your flag, so wave your flag, so wave your flag. Whoa, born to a throne, stronger than Rome, but violent prone. Poor people's home, but it's my home. All I have known, where we got born, streets we would roam. Out of the darkness, I came the farthest, among the hardest survival. Learn from these streets, it can be bleak, except no defeat. Surrender, retreat, so we struggle in, fighting to eat, and we wondering when we'll be free. So we patiently wait for that fateful day. It's not far away, but for now we say, when I get older, I will be stronger. They'll call me freedom, just like a waving flag. So wave your flag, now wave your flag. Whoa, so many wars, settled in scores, leaving us promises, leaving us poor. And in the situation where there's no compensation, they got no occupation, can buy no medication. See, it's a combination of no education. We gon' make it better, say tomorrow's generation. They can't control us, no they can't hold us down. We gon' pick it up even though we all wondering when we'll be free. So we struggling just to be free, so we patiently wait for that fateful day. It's not far away, but for now we say, when I get older, I will be stronger. They'll call me freedom, just like a waving flag. So wave your flag, now wave your flag, now wave your flag. Whoa. Probably the sound would be better with a guitar right next to me, but it's the best I could do. Yeah. So now you guys get to listen to some more songs.
Hi guys, how are you all doing? You guys look like a tough crowd.
That's what I said too.
Yeah?
I heard them play. I said, you guys, you better do something about this. So
Yeah.
hopefully
2A was great.
now, they're great too.
You guys are awesome as well.
But they have to do something about it.
You guys need to top 2A. Hi Jennifer. Oh, I'm sorry. My name is Cherie. I will be singing for you guys today.
And my name is Yuan, like you win. Woo. So we're gonna sing 3 songs today, but it's going to be a surprise. Okay.
Don't know how you met me, you don't know why. You can't turn around and say goodbye. All you know is when I'm with you, I make you free and swim through your veins like a fish in the sea. I'm singing, follow me, everything's alright. I'll be the one to tuck you in at night. And if you want to leave, I can guarantee you won't find nobody else like me. I'm not worried about
if you guys feel like dancing, you guys are more than welcome to join. Okay, this is gonna be our last one. On your midterms. Okay, so there's this thing that I'm doing. It's called the Music Club. You guys have probably heard about it if you guys were here last year. We haven't had any meetings yet, but when I do, if you guys are interested, shoot me an email. So the Music Club is basically, just like we're trying to get a network of musicians going. So like if you're a musician and you just want to jam or sit around and listen and talk about music or like just jam for fun. Music Club, check it out. Shoot me an email. And yeah, that's it. Big dancer, by the way. Yeah, stop.
Okay, let's do the big program now, right? From part 3. Let's do this program. Very nice. Right?
It will be a very similar example in your exam. Very, very similar. If you know how to do this, you will be able to do, I think, 2 of them. A lot of points. Come on, you guys write quickly. Okay, what is that, huh? Let me see what that. It is to draw the cell, draw it. Ready? Okay, let's go for it, right? So we have a galvanic cell, right? Produce a positive voltage, that's a reminder to you, right? When you have a galvanic cell, you write the when you write the equation, the overall equation of the cell, the dots, right? If it's a working galvanic cell, then the standard cells will be positive, right? And you have a reduction motivation. So here, it gives you one of the two equations that is taking place. It doesn't really necessarily to you that this is the one that takes place. It could be the reverse, we don't know, right? It just gives you an equation here. This is a reduction standard potential for this half reaction. You know what it means, right? That number compared to the hydrogen electrode, right? So we know this, but we don't know if this is the reaction that's taking place. Could be the other way, right? This half reaction, we don't know yet. And there is another reaction taking place, and that's one. It talks about what? Dichromate ions and chromium. Yes? Well, now, what we want to do is, we need another equation because there's an oxidation and reduction. We have another equation, half equation. And the question is, which one? Well, there is chromium here at 3 and dichromate ions. So you go on the back of your exam, if that was a problem, and you find out chromium 3 plus and dichromate. You have this equation, which is plus 0.133 when it's a reduction. Can you see that? Plus 1.3 when it's a reduction. If I put this in oxidation, it's going to be minus 1.3, correct? Okay. So remember that. You have that equation to use because it's talking about here. So now, we have, for this reaction, which is the reduction, just like the other one, right? We have, for the other one, we have 1 plus 1.3, yes? And this is plus 1.4. And we need one to be oxidation and the other reduction. And one has to be reversed. If it's a working galvanic cell, the sum should be positive. So which one am I going to reverse? This one or the other one? The other one, because that will be minus 1.3 plus 1.4. That will give me positive, which has to be because it says working galvanic cell. So I reverse the other one, and therefore this will be the reduction, and the other one will be the oxidation. So for the anode then, you see, here it says anode, I'm going to put the other one in a reverse way, correct? Okay, so you just copy the other one from the back as the reaction taking place at the anode, which is going to be an oxidation. So you really have this one. Forget that 5, don't put it now, we're not there yet. Just put the equation down. That's, just copy it, right? Just copy it. Okay, so we know at the anode we're going to have this oxidation half reaction, and therefore we said already the other one will be the reduction. Okay. So now we want the overall reaction, right? The overall reaction is going to be same number of electrons, both sides, right? So I have a 6 here and I have a 10 there. Can you see that? They have to be the same. So I multiply this by 5, every coefficient by 5, and here every coefficient by 3, because that will give me the same number of electrons. I add them. You don't touch this. These values represent standard states. They don't depend on these coefficients or on concentrations. They are not dependent on concentrations. It's defined by standard states. 1 molar, 1 atmosphere, blah, blah, right? So when you do that, you will have this final equation with this standard cell potential plus 0.15. That's the way we wanted to have it because it's a working galvanic cell, right? So we already did B2 because we calculated the standard cell. So the next thing is we write what? The cell description in abbreviation notation. So, what do we do? Anode on the left, cathode on the right, correct? Yes? So if the anode is on the left, that will be the oxidation. Yes? So what's the oxidation here? This one. Okay? So this is oxidation, that will go on the anode, on the left. Do you see any solid? No. So you have to use platinum, right? Then vertical line, the interface, then it's the solution of the half reaction that is taking oxidation place, right? So I'm going to put this, and that, all of them, comma, right? Comma. And then we have the bridge, and then we're going to have the cathode, which is the reduction. This is the reduction. So I'm going to have what? Do you see any solid here? No. Okay, so we're going to start after the bridge, the two vertical lines, and we're going to start with the solution. So it's going to be this, that, and that. We put everything except the water. We don't put the water. Okay? Everything else we put. And then will be a vertical line. That's the interface between the electrode and the solution. And because there's no any solid here, what I'm going to put again? platinum. Yes? So I should be looking like this then. So the answer should be this. I don't care how you put this in order here, it doesn't matter. Some others try to make a rule, but they don't agree with themselves, so I don't care. Doesn't matter how you put it. I don't know. Depends what when we talk with my head here, what we decide. What did we say in lecture? Did we say in lecture what we do? No, so probably we will not take days off. We will not take days off. Quite so. Okay, let's go to the next. D. What's D? Yes. No, that's not an equation, that's a notation. Right? All right. Let's go for the... Yes. That's the way it's in the equation, as you can see. That's why you put it. Whatever you see here, you put there. Okay?
Question.
Yes.
Isn't the phase separated by a line? Phases between aqueous and the liquid?
Where?
At rooming and then...
Here, you mean?
Yes.
All these three these should be here, comma. I forgot to put it, so I put it by force on the bottom. Should be this, should be comma right there, okay? The same thing with this, comma, right somewhere there, okay? I forgot to put it, that's why I put it on the bottom, yes. If you would be wrong, what? No, you put commas, that's the convention. You put commas, okay? Oh, I see what you mean. Here you mean? Oh, maybe you're right. Let's see. I think you're right. Yeah, I didn't notice that. It's a different phase. Yes? I think it should be that way, yeah. So this goes here, right? And then you have a line there, right? That's what you're talking about? Okay. Yeah, I didn't notice that. Okay. So let's go for the D. So for the D, you just have to really do calculations, not a kind of any big deal about it. You use the equation we know, right? If you know the cell, you know the number n. You remember, the number n depends on the way the equation is written. Because that equation can be multiplied by any number you want, still will be correct. But you use the lowest numbers, integer numbers, right? And that's why you have how many electrons there? 3. Otherwise you multiply, you change the number n. If you change the number n, what are you going to change? The equilibrium constant. Can you see that? And many books, many others do not really emphasize this. They don't make a point about it, but the value of the equilibrium constant depends on the way the chemical equation is written. I'm not talking about this or that, reverse. I'm talking about the coefficients. If they're multiplied by 2 or 3 or whatever, right? The equilibrium constant depends on this. So that's why it's important. You put the smallest integer numbers. When you do that, with the way we did it, it comes out to be that way, right? And then you take that number of electrons of the overall equation that you eliminated. That's the number that you put for n. Okay? And then you very easily you can find out the equilibrium constant. If you find the equilibrium constant, you can find delta G standard from this equation, or you can find it from the thermodynamics came to be equation, you know, right? Delta G standard minus R gas constant times T Kelvin times natural log of K. Remember? So either way. So you can see the equilibrium process is amazingly large, tremendous, huge. What does it mean? That this reaction has an incredible driving force to take place. It doesn't mean it's going to take place, only if kinetics allow it. But it has a very large driving force, tendons take place. That means if kinetics allow it to take place, and it's finished and reached equilibrium state, and you start with stoichiometric amounts, there will be no reactants left, practically zero, nothing, only products. That's what it means. K equilibrium so large, right? You realize that? Okay. What's the other? The other question was what? E. That's that's a good one. So the other question was to calculate the voltage of the cell when all ionic species except proton are 0.15 instead 1, right? And pH is this, minus point. I put it on purpose minus because many people think that pH cannot be minus. Okay? So, I want you to notice something here. Because you could, sometimes you can predict, right? And you can check if you have a correct number or not, so you will not make a mistake. If you look at the equation, yes? Where are you? Okay. You control the pH. Okay? So you assume that you have a buffer solution and the pH stays the same when the reaction is taking place. Okay? Or you have that pH when it starts. So you're talking about now it starts, right? So the pH is this much, okay? So the moment that it starts and the pH is this, what's the potential? Okay? That's the question. So I want you to notice this. Here is the equation. Here is the overall equation, right? And when you have the two cells, and this is 1 mole per liter, molarity 1, they're all 1 molar, yes? Then, this is the driving force for the reaction to take place. Plus 0.15 volts, yes? That indicates to us that it has a tendency to go from left to right, yes? That much. Relatively speaking, with other reactors, right? Now, 1, 1, 1, 1, everything is 1 in solution. When I go to what the problem is talking about, all ionic species, what? 0.15. I don't know the H plus because I have to solve this. But I can solve this and I can find out the concentration of hydronium ions. So if you do that, you find out that the concentration of the hydronium ions is 2. Okay? Very easy. From here you find 2. So really, you have, look, this is 0.15, that's less than 1, yes? What does that do according to Le Chatelier's principle? It's going to make the system to go to the left or to the right. When all is 1, and you have this driving force, and now I lower the concentration of the reactant, the system is going to go towards the left or the right. Le Chatelier's principle. How many people say left? How many people say right? How many people do not know? It's going to go to the left. When you decrease the concentration of the reactants of a system that's in equilibrium, or even if it's not in equilibrium, right? You will reduce its tendency to go to the right, or if it's in equilibrium, you will make it go to the left. Yes? Did you hear that? This is Chem 2B stuff. And I know when we hear it for the first time, we don't understand it. That's the general rule. So maybe now you can understand it. If it was a system, right, 1, 1, 1, 1, and has the tendency to go to this way, and I reduce the concentration of the reactants, or I increase the concentration of the reactants, if I increase the concentration of the reactants, or for 1 at least, or I reduce the concentration of the products, then the system will have greater tendency to go, yes? If it's in equilibrium, it will remove its equilibrium position from left to right. That means the relative amounts of the reactants will change and we'll have more products than reactants. If the system is in equilibrium and I reduce the concentration of the reactants or I increase the concentration of the products, then the system is going to go from right to left, right? If it was already a tendency to go from right to left, now we will have higher tendency to go from right to left. Yes? Okay, this is very important to realize from Keq to B. Now, by reducing this, you make the system to go that way. This, that way. This is higher. It tells the system to go that way. So all these three changes, they say the system go that way. If this was also more than one, then everybody says go that way, and so this will have less tendency to go towards the right compared to 1, 1, 1. And this would be more positive or less positive? Less positive, 0, or even minus. Depends how much of these forces, the lowering of the concentration would be, correct? But now that 3 of them, they say go that way, and 1 says go the other way, I don't really know what's going to happen. I need numbers, otherwise I don't know what's going to happen. So now I cannot predict. But if every change was telling go that way, then I would know that it will be less positive, maybe 0, or even negative. If all the arrows will go that way, it would be more positive than what it is. You got it? Okay, so now we do not know, we cannot predict. So we don't know what's going to happen. It could be more positive, could be less positive, could be 0, could be negative, we do not know. Okay? So if you do the calculation, you need to use Nernst equation, right? The Nernst equation. So to do that, you need the Q. You need the reaction quotient. So you go to the equation, the reaction quotient is exactly the same expression, mathematical expression, as the equilibrium constant. So you're careful with the coefficients. Look, there are some crazy coefficients there, right? Crazy powers. But nevertheless, the number that comes out is not that, it's a normal number. Well, normal is very large, right? Very large. Compared to the equilibrium constant, how much is that? Oh, that's much smaller than the equilibrium constant. So, what does it mean? Going towards equilibrium, you're going to have to increase, right? Okay, so this is the Q. If you take the equation now and put it in, you have that on the back of your exam, you find out that the E cell is positive and it's less, right? Isn't it? Yeah, it's less. So the 3 changes that we did, going from right to left, they overweight, right? The change we did to go from left to right. The 3, it could be the other way around. It could be just that change for this way to overweight the other 3 ones. We don't know, right? That's why I need to calculate Q. Okay, and so the last thing is what? The last thing is to draw the cell. Can you draw the cell? Can you do it? So you can check it out. How do you do it? You're looking at your equation. If you look at your equation, then you will be able to do it. So here is the equation, the overall equation. How do we draw the cell? You have one problem with 6 points, I remember now, 10 points. The last problem, to draw a cell, okay? It's very easy. Okay, look. You can look at the overall equation or you can look at here. It doesn't really matter. Maybe I think it's easier to look at here, right? If you look there, it's easier. So here is one. Here is the other. Here's my bridge. I like to do my bridge like this. Here is the membranes, right? And here's my solution. Here's one, here's the other. Here should be the anode. and here should be the cathode. Why? By convention, that's all. It's not a big mysticism here. It's by convention. When I draw the cell, I will put the anode on the left and the cathode on the right. Now, here is one electrode, here is the other electrode. What do I see? For both, I see platinum. Okay, so this is platinum and this is platinum. Big deal. Okay? Here's the wire. And then, by convention, at the anode, we have the oxidation. So which is the oxidation? Let's see. At the anode, the oxidation takes place. So chromium 3 plus goes. So I have the chromium species. So all these three are going to, this should be here. So I'm going to put chromium 3 plus aqueous, dichromate, and hydronium ions. All these three should be there. Well, then the cathode is the reduction, so it will be the bromates, hydronium ions, well, if you want to put bromine here, liquid, you can put bromine liquid. Here we're going to have potassium chloride, usually we use potassium chloride. Let's go to the signs now, right? If this is the anode and there is oxidation, then this is going to be minus or plus. This is going to be plus. So if this is minus, the plus should be going towards there, and this is plus, the minus should be going towards there. Yes? That's the direction of the ions, moving. And the electrons are going to go this way or that way, from left to right or right to left. There's a lot of electrons here, there's not many electrons there. Well, then the electrons should go like this. So minus charge is moving like this. The minus charge is going like this, right? You want another problem? Or you want to go home? How many people want another problem? Raise your hands. How many people want to go home? All right, we're going to do another problem. What's the question?